This one's looking for the instantaneous velocity at x equals 2 for the function f of x equals x squared. So let's plug in values very, very close to 2 and figure out what that is. I'm going to choose f of 2.00001 minus f of 2 all over, and remember, since we're picking something very, very close to 2, we can really just simplify this into how far away from 2 we did it. So let's plug in these values and find out what we get. In this case, after you square 2.00001, you'll get this value, and then squaring 2 obviously gets you 4. Subtract those, you're left with this, divide by that, and you get an instantaneous velocity of 4. And we'll see how that is, or we'll see why that is, because of derivatives. Today we'll be looking at derivatives, and these are a wildly important topic in all of calculus. So there's a lot of different ways you may see derivatives listed. Like here, they could have a little prime next to the function name. You could also see df dx, which stands for the derivative of the function f with respect to the variable x. And a very common one is this, which is again the derivative of y with respect to x. You'll see that one a lot. Basically, if you see d something over dx, it means you take the derivative with respect to x, which is basically all we're going to do for the beginning of this. Now, in terms of limits, the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. You may remember this as the instantaneous velocity formula. Wow, crazy. So, there's another way to think of this too. It's also the slope of the tangent line of the function. So if you have this function here in blue, and we're looking at this point, we want to find the instantaneous velocity. Now remember, if you were trying to find the average velocity from, say, here to here, you would just draw a line between those two and figure out what the slope is. It becomes a little more complicated when you're only dealing with one point, so you need to use the tangent line. The tangent line just touches the function once at the point itself, and then kind of roughly approximates the slope of the function at that time. That's what the derivative finds you. The derivative function will give you the function of this, the slope of the tangent line. And if you plug in the x value, you can find out what that slope actually is. Now, let's figure out how to do it. That feels more important. So, there's a power rule for very basic derivatives. And the rule is this. The power of x in the derivative is 1 less than the power of x in the original function. So basically you take whatever the power is and reduce it by 1. And the coefficient of the power of x in the derivative is the same as the power of x in the original function. Some kind of weird words, but think of it this way. If you have x to the n, what you do is you take that n, you move it out front as a coefficient, and then you subtract. So here, let's do a couple of real quick examples. How about if f of x equals x to the 10th? What you do for the derivative of f of x, notice the little prime there for the derivative, you take the exponent, make it the coefficient, and then reduce the exponent by 1. Now here, let me throw one at you here. What about f of x equals x? Well, the derivative of this, the exponent is 1, and then you reduce that to 0. So you have 1 times x to the 0. Well, anything except 0 to the 0th power is 1. So you have 1 times 1, or 1. And now, this one comes up a lot. What if you have just a constant number, like 7? Well, you could rewrite 7 to be 7 times x to the 0, because that's just 1. So what you would do here for the derivative, you would have 0 from the exponent times the 7 that was originally there. And then you'd have x to the negative 1. But hey, let's face it, you got 0 right there. That just means this derivative is 0. So anytime you're looking at just a constant number, the derivative is always 0. Okay, let's try a few more right here. So for x to the 9th, that one's pretty straightforward. You bring down the 9, and then x to the, subtract 1, 8th. G of x is a little complicated. Now, we're going to have to deal with a little power rule thing. G of x, I'm just rewriting it here, not even taking the derivative, is x to the 7 over 5. Remember, this is the power here, and this is the root. The root always goes in the denominator of the exponent. So now, to take the derivative, we follow the same thing. Bring out 7 over 5, x to the, and just a little sidebar over here, 7 over 5 minus 1 is like 7 over 5 minus 5 over 5, which is just 2 over 5. So there's a quick sidebar. So it's 7/5 times x to the 2/5. And over here, let's rewrite this h of x too. H of x, if you remember, can be rewritten as x to the negative 8th, because 1 over x to the 8th. So to take the derivative of this, you just follow the same rule. Negative 8 times x, and be careful with your negatives. 1 less than negative 8 is negative 9, which if you want, you could rewrite as negative 8 over x to the 9th.